Now, in a finite dimensional complex vector space, the number of vectors is infinite. But if that finite dimension is D, then we can find a basis of D elements, and every element of the vector space is a linear combination of those D basis elements. Now, in representation theory, the number of representations of a group is infinite. But it turns out that there's a finite set of representations called irreducible representations, so that all the other representations can be described in terms of those irreducible representations, kind of like a basis of a vector space. And since there's infinitely many representations, there's also infinitely many characters. But we'll look at how to describe all of them using just a finite set. So recall our definition of representation and character. Let's let V be an m-dimensional complex vector space. And let's let rho be a map from G to GLV. Well, a homomorphism. Let's let that be a complex representation of G. Then we define the function chi rho from G to the complex numbers, taking an element G to trace of rho of G. This is called the character of rho. Now, group characters are trace functions because we defined it that way. But not all trace functions are group characters. On the other hand, all trace functions live in the trace space, which has dimension equal to the number of conjugacy classes of G. So the question is, which traces in there are actually group characters? They've all got to be in this space. They're in there somewhere. Maybe they form a subspace. Actually, we're going to see they don't actually form a subspace, but they form something else. They form a sub-something. So which traces in T of G are group characters is the question. So to answer this, let's look at a couple of things that we can do to group representations to get other group representations. So we'll come back to this question soon. But first, a fact. So let's define rho as before. And rho is a map from G to an m-dimensional complex space. let's take this definition of row, and every time we get a matrix, let's conjugate it by a fixed m by m matrix. So let's let P be an invertible m by m matrix in GLMC. Actually, I guess I'm not using coordinates here, so I really want rho to be a representation, a matrix representation. So let's choose coordinates of V so that rho of G is a matrix. So rho is a map from G to G, L, M, C. Now let's define another representation. Rho prime from G to GLMC by sending each element little g to P rho of G P inverse. So we're just going to take the definition of rho and conjugate by this fixed number, this fixed matrix P. So P is an invertible m by m matrix. It turns out that, well, rho is a representation. I guess I gave away that punchline by saying let's define another representation. Rho prime is indeed a representation. And its character is chi rho, so the same exact character as rho. So the reason that it's a representation is if rho of G rho of H equals rho of GH, then rho prime of G rho prime of H equals P rho of G P inverse P rho of H, P inverse, which is P and P inverse cancel here, rho of G rho of H P inverse, and since rho is a homomorphism, that is P rho of GH P inverse. And the reason that the character is the same is that the trace of P rho of G P inverse equals trace of, since trace is a trace, we can break this up and put the P inverse first and then the P rho of G second. That's trace of rho of G, which is chi of G. So conjugating a representation by an invertible matrix gives us another representation with the same character. So let's call two representations equivalent if they differ by conjugation. It turns out that row 1 is equivalent to row 2 if and only if the character of row 1 is equal to the character of row 2. So one direction is obvious, and the other direction I'm not going to prove. I'm going to state a bunch of results today that I'm not going to prove. Alright, so one way to get a representation from another is to conjugate by a matrix. Now let's say we have two representations. I'm going to put them together to make a third. So let's let row 1 be a D1 dimensional representation, and let's let row 2 be a D2 dimensional representation. So these are complex representations of G. And let's call their characters chi1 and chi2. Now let's define row 1 direct sum row 2 to be a map from G to GL D1 plus D2 C by sending G, this element G of the group, to the block matrix that we make by putting row 1 of G there and then row 2 of G here, and then zeros everywhere else. Now it's easy to see that this is a representation, because if we multiply two of these matrices, we're really just multiplying the top blocks and the bottom box separately. So they're not going to interfere with each other. And if row 1 is a representation, then the top blocks are going to behave together correctly. If row 2 is a representation, then the bottom blocks are going to behave together correctly. So this is a representation with character. Now the character is the trace of the representing matrix. If we're going to add up the diagonal entries, that's just like adding up these diagonal entries and adding up those diagonal entries and adding them together. So it's just going to be chi1 plus chi2. Now we call a representation irreducible if it's not equivalent to something that can be broken up into blocks like this. So if it is not equivalent to row 1 direct sum row 2 for other representations row 1 and row 2. And while I'm stating this definition, I guess it's reasonable to note right now that if we have a one-dimensional representation, so if row 1 is a homomorphism from G to GL1 of C, which is basically all complex numbers except for 0, so 1 by 1 matrices, that couldn't possibly be a direct sum of smaller matrices because it's a 1 by 1 matrix already. So one-dimensional representations from G to C star are certainly irreducible. All right, now a couple theorems that I want to state, but skip the proofs. So the number of equivalence classes of irreducible characters is equal to the number of conjugacy classes of G. So of course these are characters of G. I'm omitting the proof. Another theorem is that the irreducible, well, I guess I meant representations there. Characters are equal, the representations are equivalent. So the irreducible characters, that is, characters of the irreducible representations, form a basis of the trace space. So there's the right number of them because the number of equivalence classes of irreducible representations is equal to the number of conjugacy classes in G. And that's the dimension of the trace space. It turns out that these irreducible characters are linearly independent, therefore they form a basis. Again, I'm omitting this proof. And then an important, probably the most important theorem in representation theory is that all representations are equivalent to direct sums of irreducible representations. So if we understand the irreducible representations, we understand everything. Kind of like a basis, but when I write it out, we'll see that it's not exactly a basis. So this theorem is known as Maschke's theorem. So if we have a finite group, it doesn't hold for all groups, it doesn't hold for GLNC, for example. If G is finite with D conjugacy classes, and let's let row 1 through row D be the corresponding irreducible representations. I shouldn't say the because these are determined only up to equivalence conjugating by an invertible matrix. So then every finite representation of G is equivalent to row 1 direct sum with itself, let's say A1 times, row 2 direct sum with itself, let's say A2 times, etc. And then row D direct sum with itself AD times. For some vector of non-negative integers A1 through AD. So every representation can be described in terms of this sort of basis, except the only linear combinations we're allowed are non-negative integer linear combinations. Of course, a basis of a complex vector space, I mean, if this were a space, we'd be multiplying by all complex, we'd be using all complex scalars. But here we're only using non-negative integer scalars. So when we take something like a basis and look at all non-negative linear combinations of those, this is called a cone. The cone spanned by these representations. Not a subspace because it's not closed under real scalar multiplication, complex scalar multiplication, certainly no negative numbers. All right, as a consequence, let's let chi1 through chi d be the irreducible characters of G. So the characters of these D irreducible representations. Now the irreducible representations are equivalent up to conjugating by invertible matrices. But no matter what we conjugate by, the trace is going to be the same. So these, there are no equivalence classes here. These are the D irreducible characters of G. So if you accept my theorem before that the irreducible characters form a basis of the trace space. So the traces in the trace space, which are characters of G, are precisely the non-negative integer span of these.